So I know these combined loading problems can be really rough. They can be really hard to understand, understanding what's positive, what's negative, putting things together. So I wanted to do just a couple more examples that, this is totally optional. You can just watch these, go through these, use these as practice problems to kind of get a better grasp if you're just looking for a little more practice, a little more help, a little more guidance in seeing how these combined loading problems work. So I'm going to start with simpler examples, and I'm going to move into two other more and more complex examples as we go down the line. But let's go ahead and jump into just this first example problem here, where we have a gondola. We've got this gondola, this little ski lift kind of vehicle, I guess. Traveling on a ski lift or something, a sky ride. A gondola and passengers have a weight of 1,500 pounds. If the suspender arm, our little blue arm here, has a square cross-section of 1.5 inches by 1.5 inches, what's the largest normal stress in region CD? So we already know we're not going to be dealing with shear stress in this. It's just asking us for the normal stress, so that's one less thing to worry about in this combined loading problem. But what we always want to do when starting these combined loading problems is, if there's not any statics really to start with, then we're going to go ahead and cut it at our area of interest and find those internal forces. So here we're interested in this region CD here. So we can take an arbitrary cut pretty much anywhere in this cross section to find our internal forces there. Right? It doesn't really matter if we're, at the 1 foot mark or the 2 foot mark in this section CD. We can just take our cut there. And I'm going to draw myself a free body diagram. So I've got the arm here, and here's my cut area. And then we have the gondola down here, and it's contributing a weight of 1,500 pounds. Right, 1,500 pounds straight down. Center of gravity, it's going through point A. It's in line with point A here. A is over B, B is over E, and then this CD is over off to the side by 1.25 feet. And that's center to center. So cross-section center to center, that 1.25 feet. So I've taken my cut, and I know that here I'm working in this kind of 2D problem space, so I really only have 3 internal forces that I'm looking at. I've got a normal force, I have a shear force, B, and I have a moment, M. Right? Normal force, shear force, V are 3 equilibrium equations we can apply to solve for these 3 unknowns. So we'll go ahead and do that. Let's start with the easiest one first here. Our sum of forces in the x direction is 0, and there's no shear, right? Shear is the only thing in the x direction, but we don't really care about shear anyways because it's only asking us about the normal stress. So that works out perfectly fine. There's no shear anyways, no shear stress. So we can move on to our next one. Sum of y forces is 0. Only got 2 things in the y direction. That is n minus 1,500. So easy enough. That normal force is 1,500 pounds. And then finally, I'll take a moment about my cut there. And that's going to give me the moment value, which the way I've drawn it, it's negative. So we'll say counterclockwise is positive. I've drawn it clockwise, so negative m. And then I have this 1,500 pound force that is, what was this distance? We said is 1.25 feet. So that 1,500 pounds pushing clockwise or counterclockwise around that cut. So plus 1,500 times 1.25 feet gives me a moment of 1,875 pound feet. That's a little messy. Let's write that better. Pound feet. Perfect. So I have the internal forces. Now I just need to decide, where is that largest normal stress going to be? What is the largest stress caused by each of these guys? So we know a normal stress causes an axial load, right? Causes an axial normal stress of N over A. And a bending moment causes a normal stress of My over I, or MC over I. You might see it either way. So I want to find the highest value for both of these, right? And then I'm going to add them together via superposition to find the largest overall normal stress. So the largest overall normal stress is going to occur when I add these guys together, right? When they're not competing with each other, they're going in the same direction and the largest value for each of them. So for my normal stress, it's the same everywhere throughout my cross-section, right? If I were to draw kind of the little square cut here, that normal force, doesn't matter where you take the point, it's always the same. That normal stress is going to be always the same. 1,500 pounds over an area of 1.5 inches squared, which gives me 667 psi, pounds per square inch. So my maximum bending stress, though, I know that varies depending on where I'm looking in my cross-section. All right, so we take a cross-section. I know that at the outer edge, it's going to be greatest. And then as I go towards the centroid, it's going to get smaller and smaller till it's 0 at the centroid there. And then it reverses direction, right? So now it's going into the board on one side, in compression on one side, and in tension on the other side, with a 0 down the centroid. So my greatest normal stress is going to occur when they're both facing in the same direction, right? This same direction on the outer edge. So I know that that's going to be on the outer edge, is where I get the maximum bending stress. It's going to be 1875 pound-feet. Let's do a quick little conversion to inches, 12 inches per foot. And now I need a Y value. So again, that Y value, that's your distance from the centroid to your point of interest. Or if you're looking for a maximum, it's distance from the centroid to the outer edge, which usually is just the centroid. So here our cross section is 1.5 inches. So that's 0.75 inches. 0.75 inches for our Y value. All over the moment of inertia, which this is just a square, so that makes it really, really easy. It's 1/12 base height cubed, just like for a rectangle, but since both sides are the same, it's really just 1/12 base to the 4th, right? Since base and height are the same, we can combine those. 1.5, or you could write it out if you want, 1.5 times 1.5 cubed. You can write it either way, it's gonna all come out in the wash. So I'm going to plug all of that into my calculator, and it gives me 40,000 pounds per square inch. I got everything in inches, everything in pounds per square inch. So again, the greatest version of this is going to be just these two added together, which is about as simple as it gets for these combined loadings. Finding the greatest, just adding those together. The greatest normal stress is going to be 40,667 psi. So if it asked you for, the stress at a specific point, then we would really need to pay attention about where that point is and whether we're in tension or compression, if things are facing in opposite directions from each other. But if we're just finding the largest one, typically we're just going to be adding things together. We're going to be finding the greatest values of each of the stresses and adding those together. Let's take a look at another example. In this example, we're trying to find the state of stress at point F given this little wooden setup that's holding this 20-gram mass that's also kind of cabled into the ground at BC here. And it's got a square cross-section, 75 millimeters by 75 millimeters, with point F being in this section AA that's a meter off the ground. And this F is offset also. It's not right at the centroid. It's 25 millimeters from the edge. So anytime we have a question that's asking us about the state of stress at a point, that's a pretty good indication that we're going to be doing combined loading, right? So state of stress is asking us just to find the normal stress and the shear stress that's going on at this specific point. So that's what we're going to do. But to do that, we're going to have to do a lot of statics first, right? We need to solve some of these reactions so we can take this cut at AA. If I just go ahead and do this cut at AA without solving any of my reaction forces, then I don't really know what's going on, right? If I cut it and I take the bottom portion, then I'm missing those reactions from the pin at A. Or if I cut it and do the above portion, I don't have that reaction for cable BC. I don't know what force is in that to be able to solve for the internal forces. So my first step here is going to be doing the statics before I can actually make the cut and do the internal forces. So let's go ahead and do those statics real quick. Give myself a quick and dirty free body diagram. Here we have the 20 kilogram mass, and that is a mass, so I need to get that into a force. And it's in kilograms, so I'm going to multiply by gravity 9.8. So 20 times 9.81 is 196.2. So I might go ahead and just put that in here. 196.2 Newton. Then I have that force in cable BC and the reactions AY and AX from the pin at A. So this should be pretty simple for you, pretty straightforward to go ahead and apply those equilibrium equations. I don't want to start with Fx. It's usually easiest to start with a moment. Do that later. Let's start with a moment. Maybe a moment about A. Take a moment about A. Let's see, this distance is 2 meters and this distance is 3 meters. So if I take a moment about A, that'll be negative 196.2 times its distance away is 2 meters plus just the x component of FBC, right? The y component of FBC would be going through my line of action of point A. So only the x component for FBC. FBC, which is the x component here, is going to come from sine 30. FBC sine 30 times its distance away of 3 meters. Plug all that into the calculator, and it gives me that the force in that cable BC is 261.6 newtons. And now that I've had that, it's going to be really easy to find AX and IY. Right, I do my sum of X forces, that's going to be AX minus the X component of FBC. So 261.6, we said the X component was sine 30. So my A reaction, X is 130.8 newtons. I do the same deal with my Y forces, AY minus the Y component of FBC, so 261.6 cosine 30. But don't forget about this guy. Don't forget he's kind of off to the side, but don't forget he's also a Y force there. Minus 196.2 newtons. Gives me an AY value of 422.75 newtons. I know I kind of sped through that, but I'm really hoping that by this point you're pretty comfortable with statics, that all of that was really straightforward. So I'm hoping that's where we're at with statics right now, and I can just jump into the next portion, which is making that cut. So I'm actually just going to delete all of this. I'm going to write down these AX and AY values, but I don't need this for anything other than those AX and AY values, which I'm going to put in a new free body diagram where I'm cutting there at AA. Okay, so I'm going to take my cut there at AA. There's my 1 meter length. AY we said was 422.75 newtons. AX we said was 130.8 newtons. And now at that cut, I can go find everything else, right? My normal force, my shear force, and the moment, M. So I'm going to go through the exact same process again, just applying those equilibrium equations to solve for these internal forces, which I know is terribly exciting. That's what we're going to do. So if I do my sum of x forces, it's pretty straightforward. I really don't need to write the equation down. I can see there's only two. There's shear, the V, and then that 130.8. So shear is 130.8 newtons. It's as simple as that. Doesn't get much simpler. Our normal force, we'll see here our sum of y forces, that I've actually drawn my normal force in the wrong direction because AY points up. My normal force is actually going to be in compression here. So I'll put this as a negative, since this is compressing, a negative 422.75 newtons. Right, same as the value below it. And then for my moment, the only thing contributing to my moment is this 130.8 newtons. And that distance is 1 meter away. So again, very easily, luckily I've drawn this in the correct direction, so it's going against the existing moment. 130 times 1, it's 130. 130.8 newtons. And that's it. It was really very straightforward reading these off. You can set up your equilibrium equations and solve them if they're not as clear to you, or if you want to double check yourself. That would be a very smart thing to do. But these are going to be our internal forces, which means all we need to do now is see what's happening at point F. So what is actually going on at F here? Right, so F is positioned right about here. Right, so we can see it's being compressed by this normal force, right? We know that normal force is going down on F. The moment is also going in the same direction, pressing downwards on F. Right, so normal and moment in this case are in the same direction. They're both compressing. If F were, say on this other side, then the moment and the normal force would be in opposite directions. They would have different signs, but in this case, they're both compressing. They're both going to be negative. They're both compressing on that point F. And then V, our shear, that's our only shear source. So we're going to apply our shear stress equation for that one, and it'll be our only one. So he'll be a little bit simpler. But let's go ahead and take care of this normal stress since we're talking about it. So looking at everything normal that's happening, I have the normal force, negative N over A, and then also compressing in is that bending moment, My over I. I'm going to go ahead and plug in everything I know for this. This normal stress at F, negative, what did we get for this normal? 422.75, since it's in compression, over the cross-sectional area. That's 0.075 meters squared, right? It's a square cross-section. And that's just converting the millimeters into meters. And then my bending moment, I wrote that this was in newtons. That's not a unit for moments. It's Newton meters. We did multiply by 1 meter. So that is 130.8 Newton meters times the distance. Now remember, y is distance from the centroid to the point of interest. So our centroid happens halfway here through this 75. So that's 37.5. And then I want this distance here. It's very small. It's a little hard for me to draw here. But we know it's 37.5 to the edge, but 25 to point F. So to get this distance here, I just need to subtract these two. 37.5 minus 25, that gives me 12.5. That's millimeters. Let's convert that over to meters. So times 0.0125. Our y value, and then moment of inertia, 1/12 base. Base is 0.075 times height, 0.075 cubed. And then I just need to plug all of that into the calculator to get a normal stress of negative 695,444. 695,444 pascals. Everything was in units of newtons per meter squared. Newton per meter squared is a pascal. You could write this in a simpler form. We could say negative 695 kilopascals. You wanted to round a little bit, simplify a little bit, but those are the same. So that's our normal stress, right? Negative because it's a compressive stress. So our last thing to do is going to be finding that shear stress. And for a shear that's just cutting through like this, we're going to use our transverse shear stress equation. Right, we really only have two main options for our shear stress equation, and it's either this VQ over IT, or if you have a torsion, you have a torsional moment, that's when we would use torque times radius over polar moment of inertia. But this one's just a transverse shear, so we can go ahead and solve for this guy. Let's go ahead, let me find my Q, kind of sidebar over here to find Q. So here's where F is. Here's my centroid, here's where F is. So I know that my Q is going to be for this area right here, because my shear is going down this way across it. So I want to use the area that's away from the centroid and find my Q for this area here. So Q is the centroid of the shaded area, right? Area above the point, away from the centroid, times that area. So centroid of this area here is what I need to find, and I need to find the area of this area. So this is 25 by 75. Well, that makes the area portion easy. But this center is going to be halfway through the 25, so 12.5, but I'm measuring this distance from the centroid. So I know this distance here, or I guess I should say, I know this overall distance we just found was 37.5. So if I want to get this distance between the two, I can just subtract them. And that gives me 37.5 minus 12.5 is, oh, what a coincidence, 25. So that centroid is 0.025 times the area, 0.075 times 0.025. Which I plug into the calculator, and it gives me 4.6875 times 10 to the negative fifth meters cubed. Right, I converted everybody into meters. Q always has units of meters cubed. And now I think I'm ready to plug everything into the shear stress equation. He's the only guy. I don't need to worry about signs. It's the only shear that's happening here. So he's going to be, what did we find for that V? 130.8. 130.8 newtons times the Q value we just found. All over the moment of inertia, which we did kind of just find. We wrote it out over there, 0.075. I'm going to simplify this to be to the fourth. So it was 0.75 times 0.75 cubed. And then the thickness, the width here, right, the width at our point of interest is also going to be 0.075, right? It's that whole entire width. And I plug all of that into the calculator to get a shear stress of about 31,000 pascals, or 31 kilopascals. Either way is fine, you can write it either way. So you can see we had two different stresses going on. We had the normal stress and the shear stress in this one, contributing to different things, right? So they don't get combined. They stay as a normal stress and a shear stress. And it was just a matter of kind of finding all of those ingredients that we needed to find the stress at that point F. This will be our final example for this video, and probably the hardest one. This is a very difficult problem. We've got a sign here that weighs 1,500 pounds and is subjected to a wind pressure of 150 pounds per square foot, and we want to know the state of stress at point D. So point D is down here. This is our point D at this little cross cut right here. So we want to know the state of stress at point D there. And the first thing that we're going to need to do is, of course, some of our statics. Now, thankfully, we don't need to actually find these reactions down here, because if I draw a free body diagram for this top portion here, I'm going to simplify this down some into my little flag sign, my cut here, the section of interest. I can simplify this pressure, pounds per square foot, by multiplying by the area of this sign. So that 150 pounds per square foot times 12 feet times 6 feet. That's the area of the sign there. So once I do that, I'm going to get a net pressure there. It's acting kind of like a distributed load, right? So it's a distributed load that we're just simplifying to act in the very center there of this sign. That would make this distance, 6 feet. 6 feet, this distance, 3 feet, and 3 feet, and this distance is also 3 feet. But that 12 times 6 times 150 gives me a force of 10,800 pounds. So we've got that from our pressure. Now our problem statement also told us that the sign weighs 1,500 pounds, which is going to act at the center of gravity of the sign. So it's going to act in the very center of our sign here, 1,500 pounds. And those are really all of the forces that I have going on external. Everything else is going to be an internal force. So there's no other forces to solve for except for the internal forces here. So it was really good that I could make this cut without solving for any reactions first. I can just solve for the internal forces, which in this case, we have the Fx, we have the moment that goes about the x-axis, we have Fy, and then we have the moment that goes about the y-axis, and then we have Fz. And of course, the moment that goes about the z-axis. So this time we're working in a lot more 3D space. We have 6 unknowns and 6 equations that we need to apply. And I think really the only part that tends to trip people up on this solving the internal forces is when you're taking moments about these X, Y, and Z, they are moments about the axis. So they are not a moment about the point here. We are taking moments about the x-axis, about the z-axis, about the y-axis, moments about the axis itself. If you point your thumb in the direction of the axis, any moment, any force that curls around that contributes to the moment. So you can think of your thumb as the axis, and any forces that don't intersect it, right? We don't want anything that intersects it or is parallel to it. Anything else contributes to that moment about the axis. So in this case, let's go ahead and do our forces first. That's probably our easiest. So sum of x forces, we can see that there's only 2 forces in the x direction, our Fx and our 1,500 pounds. So that tells us that our Fx is actually pointing in the wrong direction. Our Fx is actually compressive. Negative 1,500 pounds, right? Because we've got our 1,500 pounds pointing down. Fx should be pointing up to account for that, for our equilibrium setup. For Fy, we have that 10,800 pounds going in the negative y direction. So that means our Fy must be 10,800 pounds, right? Balances it out. And even simpler than that, no forces in the z direction. Fz is the only force in the z direction, which means it's not really there. So no Fz in our scenario. Next, we'll go ahead and do the moments. All right, so I'm going to take a moment about the x-axis. If I point my thumb down in the direction of the x-axis and curl my fingers around, I can see that there's only one force contributing to that, right? 1,500 pounds does not contribute because it's parallel to the x-axis, but this 10,800 pounds does. I'm going to multiply this 10,800 pounds by the distance, which is 6 feet. And that's going to give me my moment about x. And of course, this 10,800 is causing a clockwise rotation. So that means that my moment about x is going to be positive. So 10,800 times its distance away, 6. 64,800 pound-feet, right? Those were pounds multiplied by feet. 64,800 pound-feet. And then I'll do the same for my y moment, right? If I take my hand in the direction of the y-axis and curl my fingers around, the only one that's not parallel and is contributing is going to be the 1,500 pounds. So 1,500 pounds times its distance away from the axis, which happens to be 6 feet again. So my is going to be 1,500 times 6, which is 9,000 pound-feet. And then my final one, mz, which ones I have contributing to mz. Notice my 1,500 pounds actually intersects the z-axis. It can be a little bit hard to tell from the pictures, but if I were to kind of extend both of these lines out, I would see that their lines of action are actually intersecting, which means that it's not contributing to the moment. The only thing that would be contributing to the moment is this 10,800 pounds, and this distance here from this force to the z-axis is 3 plus 3, 6 feet once again. Now notice that this is actually going in the same direction that I've drawn mz, which means my mz is negative. Negative 10,800 times 6, negative 64,800, right? We want them to go in opposite directions. They're counteracting, they're reacting to those forces. All right, so I have all of those internal forces now. Now it's a matter of figuring out, okay, what is each force contributing to? Is it a normal stress? Is it a shear stress? What direction is it going? What sign does it need to have? And then finding all of those things that I need for the stress equations. So let's just kind of break down each of these and see what they're contributing to. So let's look at this Fx first. This Fx is a force going straight down. It's in the longitudinal direction, which means that it's an axial load. That's the kind of load it's contributing, axial load. So this axial load that's acting in a compressive way, right? It's compressing it because it's negative. So my Fx is going to be a normal force, right? Axial load. So this first guy, go ahead and label him. He is a normal stress and he's in compression, right? He's negative. So I'll just put, I'll just leave normal for now. So he's a normal force, N over A. Now how about Fy? Fy, he is in the same plane as the cross-section face, which indicates to us that this is a shear stress. This is a transverse shear. So this one is contributing to transverse shear. We know is VQ over IT. VQ over IT. All right, FZ is 0, so there's nothing going on there. Going on down the line, MX. MX is a moment about the x-axis, about the longitudinal axis, and we know that if a moment's going about a longitudinal axis, that is a torsion. That is a torsion. So mx is actually a torque. We could say T equals mx. This is a torque. A torque and a moment are the same thing for our math and tensor purposes. It's just actually causing motion. So this moment is actually a torque. So this is another shear stress, but now this time it's the torque equation. Torque times radius over polar moment of inertia. That's our mx. Moving on down the line, my. My, we can see my is in the same plane, right? It's on Fy. Fy and Fz are both on the plane of the cross section, which means both my and mz are going to be bending moment stresses. So both of these guys, both my and mz are contributing bending moment stresses. So if I wanted to add all of these up and kind of put them in their superposition form, I can go ahead and do that. Where my normal stress is going to be normal over area, where that normal is Fx, plus the two bending moment equations, where this is my and mz. Then we have our shear stress equation, VQ over IT, plus that torque equation there. So there are two kind of ways, well, there are several ways that you can go about your next steps here. Right, we've set up the two basic equations. Now we just need to figure out what ingredients are going in those equations. And one of the ways that I like to do it first is I like to see which terms are going to go to 0. Because we may not actually need all of these terms. They may not actually be contributing at this point D. So let's go ahead and kind of break down each of these and see what they are contributing. So looking back at that normal force, if I go ahead and break down what's happening there. Right, so I have my, this is kind of my cross section. There's the pipe going up. I know that this is in compression. So what I'm seeing with N over A is I'm seeing a constant compressive force everywhere on that cut cross section. So I know that it's going to be contributing. Since our point D, it doesn't matter where our point D is, but our point D is, you know, down here. There's D. Everywhere it's the same. So we know that's definitely contributing. Take our pipe again. We've got, oh, and I'm just realizing I didn't put my radiuses on here. But the outer radius is 3 inches and the inner radius is 2.75 inches. Okay, well that'll help us. It is tubular. Totally tubular. Alright, so this next bending moment, MY. MY. What do we have going on at MY? If I kind of put in, here's my z-axis. Here's my y-axis. My point D sits right here. What is going on with MY? Well, MY is contributing a bending stress. So what it's doing is we can see it coming up on one side of the y-axis and then coming back down over the other. It's dolphining over the y-axis. Right, so what that looks like is I have this compressive stress on one side goes to 0 at the centroid, and then it goes to tension on the other side, right? All humping over that y-axis there, right? Little dolphin comes out of the water, goes back into the water, right over that centroidal axis, that centroidal y-axis. And since D is on that y-axis, it's on our centroidal axis, there's actually no bending stress from MY. So this whole term, we can go ahead and take to 0. It's not actually there. I'm going to do that in a brighter, boom, 0. 0. There's no bending stress there on that y-axis for point D. If we were looking at one of these other points, we might be interested in it, but at point D, we're not. So that term is going to go to 0. But let's check out MZ. What's going on at MZ over here? And so here's our cross section. At MZ, now we're dolphining over the z-axis. So what we're getting, let's see, this MZ is negative, so it's actually opposite of the way that I've drawn it. Right, this is the actual orientation, which means it's compressing up on this backside over here. And then it gets smaller as we get towards the centroid, and then it switches direction. Right, switches direction there for our Y. Did I draw this backwards? No, I do this. Okay, no, this is right. This is right. This is where our point D is. It's experiencing a maximum tension. It's experiencing a maximum tension here at point D from MZ. Right? It's compressing on the upper side, and then as it comes down from that negative, tells us we were pointing the wrong way. This is in tension. This is being pulled down at point D. So what that tells me when I'm looking at my signs for these things is I need to make sure that my normal force is negative. It's a compressive. But this MZ is in tension. It is an addition. It is positive. It is causing tension on this cross section. Where this MZ times Y over moment of inertia. So I can go ahead and find all of these ingredients. And we might as well, because we're pretty much halfway there. So I can find everything that I need for this. Which I'll go ahead and write these. Let's do these over on the side. I'll just do, how about a nice light purple? grab some of these values that I might want. So area is pi r outer squared minus r inner squared, right? Because it's a tube. So that is pi 3 squared minus 2.75 squared. Gives me an area of 4.561 inches squared. Moment of inertia for a tube, pi over 4 times r outer to the fourth minus r inner to the fourth. That's 3 to the fourth minus 2.75 to the fourth. So my moment of inertia is 18.7 inches to the fourth. And then finally, polar moment of inertia, which is the same equation as moment of inertia, but pi over 2 instead of pi over 4. So I know that that's just going to be double the value. So 37.4 inches to the fourth. And I guess I skipped a step. I don't know if I needed to calculate this J. I just went ahead and calculated it. But we can go ahead and plug things into that normal equation now. So we can solve for normal stress. Negative, that normal force was 1,500 pounds over the area, 4.516 inches squared, plus mz, 64,800 pound-feet. Let's convert that out of feet, 12 inches per foot. And then y, my y value, distance from centroid to the point of interest, is going to be 3 inches. It's the full radius. All over moment of inertia, 18.7. I pop that in a calculator to get my answer for normal stress, which is about 124 KSI, kips per square inch. So I got a much larger value in PSI, pounds per square inch. This was all in pounds. I went ahead and simplified to KSI since a kip is 1,000 pounds. About 124 KSI. Great, so that's one portion of it done. All I need to find is the shear stress. So let's continue on down, figuring out if we need all of these shear stress terms. Do we need both of these terms? So let's see, we have a torsion and we have a shear stress. Let's go ahead and look at this Fy transverse shear first. All right, so VQ over IT. VQ over IT. If we remember, for our transverse shear, anytime we're looking at transverse shear, it is 0 on the edges, gets larger as we get towards the centroid, and then smaller until there's no shear stress at the edge, which our point D here is at the edge, right? There's no way to calculate a Q value for this D, for this Fy that's going in the direction of the y-axis here. Fy, here's point D. This is in line with the y-axis, which means there's actually no shear happening from Fy. Right? No shear stress. Q value is 0. Do not need this term. Excellent. Wonderful. We love to see it. Let's see if we need our next one. All right, look at this cross section. Here's the tube or whatever. Point D. I have a torque. Right, I have this mx causing a torque on the cross section, and we know that a shear stress from torque is 0 at the centroid and gets larger and larger and larger shear stress until we get the largest at the outer edge, which our point D is at the outer edge, which means we do need this term. We do need torque times radius over polar moment of inertia. So that's our only component of this equation. So we can just plug everything in now. I did find polar moment of inertia. I'm happy we needed it. So our torque is just going to be that moment value. That moment value is 64,800 pound-feet. Convert that into inches times the radius, right? So the radius being radius from the center to the point we're interested in, which is the full radius here, so 3 inches. Over that polar moment of inertia, 37.4 inches to the fourth. Punch it into my calculator and get about 62 kips per square inch. 62 kips per square inch. And both of these worked out to be positives, right? This compressive normal stress was much smaller than the bending stress, the 124 KSI, and our shear stress was 62 KSI. Now, I would say this is about as difficult as problems in our class are going to get. On an exam, I would never give you something this difficult because, oh my God, you'd never finish the exam. But it's really good to know how to do these things, especially as you move up into tougher classes. It's really good to have these problem-solving skills, these analytical skills of how do you actually go through and solve these things? How do you approach these problems?